Hello friends, welcome you all in the video lecture series related to heat and mass transfer. We are dealing with the convection chapter. Today in this lecture, we are going to understand how to solve the problems related to forced convection. Before go to the problem, we should know that we required some properties of a fluid to solve the problems like density, specific heat, thermal conductivity, thermal diffusivity, dynamic viscosity, kinematic viscosity, and a Prandtl number. So these properties we have to find out for the specific temperature of the fluid. Now here this table is for property of air at 1 atmospheric pressure. So such a tables are there for a different kind of a fluid. If the properties of the fluids are not provided in the problem, then we have to select these properties from the table. If it is provided in the numerical itself, then we should not go for the table. We have to select the properties from the given properties only. Now these properties should be selected at a bulk mean temperature or a mean film temperature. So what is meant by mean film temperature? It is the average of surface temperature and the fluid temperature. So that is nothing but mean film temperature. So all the properties we have to select at a mean film temperature. Say the temperature of the fluid is 60 degrees Celsius and the temperature of the surface is 40 degrees Celsius, and we have to select the properties of the fluid. Then we have to take the average of 60 degrees Celsius and 40 degrees Celsius, that will be the 50 degrees Celsius. So we have to select the properties for 50 degrees Celsius. So 50 degrees Celsius properties of air as density, specific heat, thermal conductivity, thermal diffusivity, dynamic viscosity, kinematic viscosity. In this manner we have to select. Now before we start the example, we should have some idea about the formulas which are going to be used in the problem. So first problems we have discussed about the forced convection. So in this particular problem, first variety of the problem is nothing but the flat plate, the fluid flowing over a flat plate. So in case of a flat plate, the laminar flow will be considered if the Reynolds number is less than 5 into 10 raised to 5, and if, the turbulent flow will be considered if the Reynolds number is greater than 5 into 10 raised to 5. So we have seen the numerical correlations for laminar flow and turbulent flow. Just revision purpose, I have provided this data. So in case of a flat plate, local heat transfer coefficient can be given as local heat transfer, that is nothing but heat transfer coefficient, that is nothing but h suffix x is equal to 0.332 multiplied by into bracket k divided by x multiplied by rex raised to 1 by 2 multiplied by pr raised to 1 by 3. So here h suffix x is nothing but local heat transfer coefficient, k is the thermal conductivity, x is the distance of a location from the leading edge, re suffix x is nothing but local Reynolds number, and pr is nothing but Prandtl number. In the same manner, the local Nusselt number we can derive by using the local heat transfer coefficient data. So local Nusselt number is nothing but the local heat transfer coefficient multiplied by distance from a leading edge, that is nothing but x divided by thermal conductivity, that is nu x is equal to hx divided hx suffix x multiplied by x divided by k. So by using that formula, we can say that local Nusselt number is equal to 0.332 multiplied by pr raised to 1 by 3 multiplied by rex raised to 1 by 2, where this nu suffix x is the local Nusselt number, pr is nothing but Prandtl number, and re suffix x is the local Reynolds number. Then on that basis we can find out the average heat transfer coefficient and average Nusselt number also. So average heat transfer coefficient can be written as h bar is equal to 0.664 into bracket k divided by L multiplied by Re suffix L raised to 1 by 2 multiplied by PR raised to 1 by 3. So where K is the thermal conductivity, local heat transfer coefficient given as a h bar, okay, average heat transfer coefficient given as a h bar. So K is the thermal conductivity, L is the total length of the plate, then Re suffix L is nothing but average Reynolds number raised to 1 by 2, and PR is nothing but Prandtl number. So average Nusselt number can be find out by using the equation Nusselt number is equal to HL divided by K, H multiplied by L divided by K. So on that basis we can say that the average Nusselt number can be written as 0.664 multiplied by average Reynolds number raised to 1 by 2 multiplied by Prandtl number raised to 1 by 3. Now these are related to the laminar flow. Next is turbulent flow of a fluid over a flat plate. So in this case Reynolds number should be greater than 5 into 10 raised to 5. So at that time flow will be considered as a turbulent flow. So in this case the local heat transfer coefficient will be given as H suffix x is equal to 0.0288 multiplied by K divided by x multiplied by Re suffix x raised to 4 by 5 multiplied by PR raised to 1 by 3. X is the distance from the leading edge, Re suffix x is the local Reynolds number. Now next is the Nusselt number. Local Nusselt number we can find out by using the same correlation. NUX is equal to 0.0288 Re suffix x raised to 4 by 5 PR raised to 1 by 3. And average heat transfer coefficient for the turbulent flow can be written as h bar is equal to 0.036 into bracket K divided by L multiplied by Re suffix L raised to 4 by 5 multiplied by PR raised to 1 by 3, where this h bar is the average heat transfer coefficient, K is the thermal conductivity of a fluid, L is the total length of the plate, where Re suffix L is the average Reynolds number. Now average Nusselt number can be determined by using this correlation. So average Reynolds number Nu suffix L bar, that is nothing but average Nusselt number, will be given as 0.036 into bracket Re suffix L, that is nothing but average Reynolds number raised to 4 by 5 multiplied by PR raised to 1 by 3. Now here we are going to see our first problem. So problem number 1, statement is air flows over a heated plate at a velocity of 50 meter per second. The local skin friction coefficient at a point on a plate is 0.004. Estimate the local heat transfer coefficient at this point. The following property data for air are given. Density is equal to 0.88 kg per meter cube. Viscosity is equal to 2.286 into 10 raised to 5 kg meter per second. Specific heat Cp is equal to 1.001 kilojoule per kg Kelvin. Thermal conductivity is equal to 0.035 watt per meter Kelvin. And here the relation also provided in the problem. Use Stanton number multiplied by Prandtl number raised to 2 by 3 is equal to C suffix Fx divided by 2. St is nothing but Stanton number, PR is nothing but Prandtl number, C suffix Fx is nothing but local skin friction coefficient. So the given data is provided as velocity is equal to 50 meter per second, C suffix Fx, that is nothing but local skin friction coefficient is given 0.004, density is provided 0.88 kg per meter cube, dynamic viscosity is provided as 2.286 into 10 raised to minus 5 kg meter per second, and specific heat is also provided as 1.001 kilojoule per kg Kelvin, and thermal conductivity of the air is provided as 0.035 watt per meter Kelvin. Now here we have to find out the local heat transfer coefficient. Okay, so we have to use the first equation, and equation is provided in the numerical, that is Stanton number multiplied by Prandtl number raised to 2 by 3 is equal to local skin coefficient as a CFX divided by 2. Now we have to determine the values of Stanton number, Prandtl number, and so that it will be easy to determine the local heat transfer coefficient. So Prandtl number is given as PR is equal to mu Cp divided by K, where the mu is nothing but dynamic viscosity, Cp is the specific heat divided by thermal conductivity. Put up all the data related to these particular values. So mu we have provided 2.286 into 10 raised to minus 5. Cp is provided in kilojoule, so that we have to take it in a joule. For that purpose we have to multiply whatever the value with 1000. So here Cp we have taken as 1.001 multiplied by 1000 whole divided by thermal conductivity at 0.035. So Prandtl number we are getting as a 0.654. Then the Stanton number. So Stanton number is given as, local Stanton number is given as St suffix x is equal to h suffix x divided by rho Cpv. Okay, where this St suffix x is nothing but local Stanton number, h suffix x is the local heat transfer coefficient, divided by rho is the density, Cp is the specific heat, multiplied by V is the velocity. So we have to find out this Hx. So here the density is provided as 0.88 multiplied by Cp value as 1.001 multiplied by 1000, and velocity is 50. So Stanton number we will get as a local Stanton number is equal to h suffix x divided by 4,40,044 will get the value. 44,044 will get the value. Okay. Then the formula we have to consider, or this particular empirical relation we have to consider. So Stanton number multiplied by Prandtl number raised to 2 by 3 is equal to CFX divided by 2. So Stanton number we have calculated Hx divided by 44,044 multiplied by, then Prandtl number value we have calculated over here. So we have to put this value 0.654 raised to 2 by 3, and local skin coefficient is provided as a 0.004 and divided by 2. So we can easily find out the local heat transfer coefficient value. Hx is equal to 0.004 multiplied by 44,044 whole divided by 2 into 0.654 raised to 2 by 3. So Hx becomes 116.91 and its unit is watt per meter square Kelvin. That is our first problem. Now the second problem, if you consider the crankcase of an IC engine measuring 80 centimeter multiplied by 20 centimeter, may be idealized as a flat plate. The engine runs at 90 km per hour and the crankcase is cooled by the air flowing past it at the same speed. Calculate the heat loss from the crank surface maintained at 85 degrees Celsius to the ambient air at 15 degrees Celsius. Due to the road induced vibration, the boundary layer becomes turbulent from the leading edge only. Okay, so this is the problem related to the crankcase. Here they have here it is provided that the crankcase of the engine we have to consider it as a flat plate, and the dimensions of a flat plate are provided as 80 centimeter multiplied by 20 centimeter. So 80 centimeter is the length and 20 centimeter is the width. So and it runs at 90 km per hour, and we have to consider the velocity of the air flowing over the crankcase as a 90 km per hour only. So this crankcase is cooled by the air. Okay, now here the crankcase is maintained at 85 degrees Celsius, so surface temperature will be 85 degrees Celsius, and the ambient air which is flowing over the crankcase, its temperature is 15 degrees Celsius. So T suffix S is 85 degrees Celsius and T naught is 15 degrees Celsius. Now due to the vibration induced due to the road vibration induced, and because of that the boundary layer becomes the turbulent. So here we have to check out whether the boundary layer is turbulent or not. So for that purpose, initially the given data is provided as V is equal to 90 kilometer per hour. We have to convert it into a meter per second. So 90 multiplied by 1000, that will be kilometer will be converted into meter, divided by 3600, so that hour will be converted into second. So we will get 25 meter per second. So surface temperature is 85 degrees Celsius. Ambient air temperature T0 is 15 degrees Celsius. A length of a crankcase we have to consider as 80 centimeter. It will be equal to 0.8 meter. Then width equal to 20 centimeter equal to 0.2 meter. Now here we have to find out the heat loss from the crankcase. So we have to find out the Q. Now it is also provided that boundary layer is turbulent from the leading edge. So we have to use the correlation for forced convection with the turbulent flow for a horizontal plate. So initially we have considered that the boundary layer is turbulent. So we have to use the correlation for the turbulent flow over a flat plate. So this is the equation, that is nothing but nu bar, that is average nozzle number, is equal to 0.036 into Re suffix L, that is the Reynolds number, raised to 0.8, that is nothing but 4 by 5, and PR raised to 0.333, that is nothing but 1 by 3. Okay. Now we have to determine these values. Okay, to solve this problem we require to determine the nozzle number, Prandtl number, and Reynolds number. So nozzle number, average nozzle number, is equal to H bar L divided by K, that is nothing but average heat transfer coefficient multiplied by the characteristic length of the plate, that is nothing but L, divided by K is the thermal conductivity. Then Prandtl number is equal to mu Cp divided by K. Mu is the dynamic viscosity, Cp is the specific heat, and then thermal conductivity K. Now this Reynolds number is average Reynolds number is equal to velocity multiplied by characteristic length of the plate divided by kinematic viscosity, that is nothing but nu. Now we don't know the this properties, thermal conductivity, mu, Cp, V, L, and it is not provided in the problem. So at that time we have to find out these properties by using the property table for the air. So here properties of air not provided, so we have to refer air property table for various temperatures. So properties should be considered for mean film temperature. So what is meant by mean film temperature? So average temperature of surface and the fluid. So Ts is the surface temperature and T0 is the fluid temperature. So surface temperature is given as 85 and fluid temperature is 15. So 85 plus 15 divided by 2 will get the 50 degrees Celsius. Now we have to consider the air properties as at a 50 degrees Celsius. So if you go and see the properties, air properties at a 50 degrees Celsius. So here we can say that for the 50 degrees Celsius the density is 1.092 kg per meter cube. Then specific heat Cp is 1007. Then thermal conductivity is 0.02735. Then thermal diffusivity is 2.487 into 10 raised to minus 5. Then dynamic viscosity is 1.963 into 10 raised to minus 5. Then kinematic viscosity is 1.798 into 10 raised to minus 5. And Prandtl number is 0.7228. So these are the properties of air at 50 degrees Celsius. 50 degrees Celsius properties we have to consider. That is nothing but bulk mean temperature or mean film temperature. So here we have considered the same properties. These are all the properties at a 50 degrees Celsius we have considered. So therefore we can easily find out the Reynolds number. Reynolds number is equal to velocity multiplied by the characteristic length divided by kinematic viscosity. So velocity is 25 multiplied by characteristic length of the plate or the crankcase, which is considered as ideally as a plate. So its length is 0.8 divided by kinematic viscosity. It is provided as 1.798 into 10 raised to minus 5 meter per second square. So it is provided over here. So we will get the average Reynolds number as REL is equal to 11.125 into 10 raised to 5. So this average Reynolds number, we can say that it is greater than 5 into 10 raised to 5. So the boundary layer will becomes a turbulent boundary layer. So we have to consider the formula for the turbulent flow over the flat plate. So therefore Nu bar is equal to H bar L divided by K is equal to 0.036 average Reynolds number raised to 4 by 5 multiplied by PR raised to 1 by 3. Therefore we can say that the Nu bar is equal to H bar L divided by K is equal to 0.036 average Reynolds number raised to 4 by 5 multiplied by Prandtl number raised to 1 by 3. Now we have to find out this average heat transfer coefficient. So we know the length of the crankcase as 0.8 and thermal conductivity of the air is 0.02735. So is equal to 0.036 average Reynolds number we have calculated as 11.123 into 10 raised to 5 raised to 4 by 5, and Prandtl number we have taken from the property table as a 0.7228 into raised to 1 by 3. So we can say that H bar, that is average heat transfer coefficient, is equal to 2219.89 into 0.02735 divided by 0.8. So H bar is equal to 75.89 watt per meter square degree Celsius. Okay, now we have to find out the heat loss from the crankcase, that is nothing but heat transfer rate we have to find out. So Q we have to find out. Q is equal to H bar multiplied by A suffix S is nothing but surface area multiplied by TS minus T naught. So surface area for the plate we have to consider as a multiplication of width and length. So Q is equal to H bar multiplied by H bar is the heat transfer coefficient, so it is 75.89 we have calculated over here, multiplied by length multiplied by width, that is the surface area for the plate, 0.8 multiplied by 0.2 multiplied by 85 minus 15, that is the surface temperature minus fluid temperature 15. So we will get the Q as a 849.968 watt. This is our required answer. Now we will see our third problem related to the plate. So air at 20 degrees Celsius and at the pressure of 1 bar is flowing over a flat plate at a velocity of 3 meter per second. If the plate is 200 mm wide and at a 56 degrees Celsius, calculate the following quantities at x is equal to 280 mm. Given that properties of air at the bulk mean temperature, that is nothing but 20 plus 56 divided by 2 is equal to 38 degrees Celsius, are rho is equal to 1.137 kg per meter cube, thermal conductivity K is equal to 0.02732 watt per meter degree Celsius, Cp is equal to 1.005 kilojoule per kg Kelvin, and kinematic viscosity nu is equal to 16.768 into 10 raised to minus 6 meter square per second. Prandtl number is equal to 0.7. These values, these properties of air, it is provided in the problem only for mean bulk temperature at a 38 degrees Celsius or mean film temperature at a 38 degrees Celsius. Now we have to find out the local convective heat transfer coefficient at a distance x is equal to 280 mm. Here the length of the plate is provided at 280 mm. The plate wide is width is given as a 280 mm. So that is nothing but square plate we have to consider. So length and width are equal. So area becomes 280 multiplied by 280. So we have to find out the local heat transfer coefficient at the end of the plate. Okay, and because the length of the plate is 280 mm only, and we have to find out the local heat transfer coefficient at x is equal to 280 mm. So Here it is asked that determine local convective heat transfer coefficient, average convective heat transfer coefficient, then local Nusselt number, average Nusselt number, and rate of heat transfer by convection. So here we can write a given data as L is equal to 0.280, V is equal to 3 meter per second, X, that is nothing but location of point where we have to consider the local heat transfer coefficient and the local values. So that point is at a distance of 280 mm from the leading edge. So X is equal to 280 mm is equal to 0.280. So surface temperature is given as 56 degrees Celsius and the fluid temperature is 20 degrees Celsius. So properties of air at a bulk mean temperature are also provided. So that is nothing but what? The bulk mean temperature 20 plus 56 divided by 2 is a 38 degrees Celsius, and these properties of air at a bulk mean temperature are provided. So here we have to find out the local heat transfer coefficient, average heat transfer coefficient, local Nusselt number, average Nusselt number, and total heat transfer by convection. So these 5 unknowns we have to find out. So first of all, we have to find out the type of the flow. So for that purpose, we need to find out the Reynolds number. So local Reynolds number can be determined as Re suffix x is equal to V multiplied by x divided by nu, where V is the velocity, x is the distance of that particular location from the leading edge, and nu is the kinematic viscosity. So all the values we know. Velocity is 3 into 0.280, where this 0.2080 is the distance of particular location from the leading edge. New value we have to take from the properties, that is 16.768 into 10 raised to minus 6. So that we will get the Reynolds number 5 into 10 raised to 4. So which is less than 5 into 10 raised to 5. Okay. So Reynolds number is less than 5 into 10 raised to 5. So boundary layer is a laminar. Okay. So Hx, H bar, Nu, X, Ne, and Nu bar, that is nothing but average Nusselt number, should be calculated for laminar flow only. So we have to consider the formulas for laminar flow over the flat plate. So the values, the empirical relations for the laminar flow over a flat plate, we know that H suffix x is the local heat transfer coefficient, will be given as Hx is equal to 0.332 multiplied by into bracket k divided by x multiplied by Re suffix x raised to 1 by 2 multiplied by Pr raised to 1 by 3, where k is the thermal conductivity of air, x is the location of that particular point from the leading edge, and Re suffix x is the local Reynolds number, and Pr is the Prandtl number. So all the values if you put in this particular equation, so we'll get Hx is equal to 0.332 into bracket thermal conductivity is 0.02732, and x is the distance of location from the leading edge is 0.280, and the local Reynolds number is 5 into 10 raised to 4 raised to 1 half, and Prandtl number is 0.7, so raised to 1 by 3. So we'll get the Hx value as 6.432 watt per meter square degree Celsius, where the Hx is nothing but local heat transfer coefficient. So next we have to find out the H bar, that is nothing but average heat transfer coefficient. For a laminar flow, it is given as 0.664 into bracket k divided by L multiplied by Re suffix L raised to 1 half multiplied by Pr raised to 1 by 3. So where this H bar is average heat transfer coefficient, Re suffix L is the average Reynolds number. So now here we have to find out the average Reynolds number. So average Reynolds number, as the length of the plate is 280 mm, so average and local Reynolds number will be same. So that will be V multiplied by L divided by nu. So V is the velocity 3, L is the location, L is the total length of the plate, it is 0.280, and divided by kinematic viscosity 16.768 into 10 raised to minus 6. So we'll get the average Reynolds number as once again 5 into 10 raised to 4. So we can find out the average heat transfer coefficient as equal to 0.664 into bracket 0.02732 divided by 0.280, where this is thermal conductivity and this is the total length of the plate. Multiply by 5 into 10 raised to 4 is the Reynolds number raised to 1/2, multiply by Prandtl number 0.7 raised to 1 by 3. So we will get the average heat transfer coefficient at 12.864 watt per meter square degree Celsius. Now we have to find out the total heat transfer by convection. So Q convection is equal to H bar, that is average heat transfer coefficient, multiply by surface area multiply by into bracket surface temperature minus fluid temperature. So H bar we have calculated as 12.85 multiply by 0.28 multiply by 0.28, as the width of plate only provided, that is nothing but we have to consider that the length is also equal to the width. So the square surface area we have to consider. So 0.28 multiply by 0.28 multiply by 56 minus 20. So we'll get, after calculation we will get the convection heat transfer is equal to 36.30 watt. So next is average nozzle number. We have to find out the average nozzle number. So average nozzle number, this is the local nozzle number. So local nozzle number, that is nothing but Nu suffix x is equal to H suffix x multiplied by x divided by k, where H suffix x is the local heat transfer coefficient, multiplied by x is the distance of that particular location from the leading edge, divided by k is the thermal conductivity. So this is also can be written as 0.332 multiplied by Re suffix x raised to 1 by 2 multiplied by Pr raised to 1 by 3. So we have already calculated this local heat transfer coefficient, so we will use this formula. So Nu suffix x is equal to 6.432 multiplied by 0.280 divided by 0.02732. So 0.280 is the location of particular point from the leading edge, and this 0.02732 is the thermal conductivity. So average the local heat, the local nozzle number we will get as NUX is equal to 65.92. As it is a dimensionless number, so it will not have any kind of a dimension. So then average nozzle number we can find out by using the equation Nu suffix L bar, that is nothing but average nozzle number, is equal to H bar, that is average heat transfer coefficient, multiplied by L divided by K, is equal to 0.664 into bracket Re suffix L raised to 1 by 2 multiplied by Pr raised to 1 by 3, where this Re suffix L is the average Reynolds number. Now if you put the values, as we have calculated the average heat transfer coefficient already, so that we are going to use this equation. So the average nozzle number is equal to 12.864 multiplied by 0.280 divided by 0.02732. So average nozzle number we will get 131.84. So as this is a dimensionless number, we will not get any kind of a dimensions for this average nozzle number. So these three problems are related to the plates. Now we are going to see the problems related to the flow through tube. So here we have to, before starting the example, we should look into the some important points related to the flow through tube. So in case of a flow through tube, if the Reynolds number is less than 2300, consider to be laminar flow, and if this Reynolds number will be greater than 2300, consider to be a turbulent flow. Then for laminar flow, we have to consider the problem for laminar flow through tube. So for uniform heat flux will be there, then nozzle number will be equal to 4.36. So there will be directly the value of a nozzle number if the uniform heat flux will be there. So nozzle number is equal to 4.36. For constant wall temperature and fully developed laminar flow will be there, if it will be there, then the nozzle number is equal to 3.66. And for constant wall temperature, for slug flow, Slug flow means the flow consists of two phases of a fluid, and then that flow will be considered as a slug flow. So for constant wall temperature for slug flow, Nusselt number is equal to 5.78, and we know that Nusselt number is equal to HD divided by K, where the D is the diameter of the tube. So in case of a flow through tube, the diameter of the tube will be considered as a hydraulic diameter or the characteristic dimension of that particular geometry. So here in case of a flow through tube, diameter of tube should be considered as a characteristic dimensions. Hence Reynolds number also we have to consider as a velocity multiplied by diameter divided by kinematic viscosity. Okay. So for turbulent flow through tube, the fully developed turbulent flow through pipes or conducts, and the velocity distribution will be given as U divided by U max is equal to Y divided by R raised to 1 by N. So where U is nothing but a local average velocity, then U max is equal to velocity at the center line, then R is equal to radius of the pipe, capital R is the radius of pipe, and small r is equal to distance from the ball. So where small y is equal to capital R minus R. Now in case of a turbulent flow through tube, it is difficult to derive the simple analytical expression for heat transfer coefficient and Nusselt number, but such expression can be easily found out by using the empirical relation. Now this expression is in the form of a friction factor. So the friction factor for a turbulent flow is well represented by the following empirical relation. So friction factor is equal to 0.316 multiplied by Reynolds number raised to minus 0.25 for the Reynolds number value, if the Reynolds number value is in between 2 into 10 raised to 4 to 8 into 10 raised to 4, then we can use this correlation. Then friction factor is equal to 0.184 multiplied by Reynolds number raised to minus 0.2 for the Reynolds numbers in between 10 raised to 4 to 10 raised to 5. Then friction factor equal to 0.005 plus 0.396 multiplied by Reynolds number raised to 0.3 for the Reynolds numbers in between 2 into 10 raised to 4 to 2 into 10 raised to 6. So from Colburn analogy is for the Prandtl number greater than 0.5 and less than 100. So Colburn analogy, we know that Stanton number multiplied by Prandtl number raised to 2 by 3 is equal to F divided by 8. So instead of this particular F, that is nothing but friction factor, we have to consider our second equation or the second correlation, that is nothing but friction factor is equal to 0.184 multiplied by Reynolds number raised to minus 0.2 for the Reynolds numbers in between 10 raised to 4 to 10 raised to 5. So that equation we have considered. So the friction factor value we have put up over here. So Stanton number multiplied by Prandtl number raised to 2 by 3 is equal to 0.184 divided by 8 multiplied by average Reynolds number raised to minus 0.2. So we know that Stanton number is nothing but the ratio of Reynolds number to the product of Prandtl number and a ratio of Nusselt number to the product of Prandtl number and a Reynolds number. So the Stanton number we have written over here multiplied by Prandtl number raised to 2 by 3 is equal to 0.184 divided by 8 multiplied by Reynolds number raised to minus 0.2. Therefore Nusselt number, if you arrange this equation in the form of a average Nusselt number equal to 0.023 Reynolds number raised to 0.8 multiplied by Prandtl number raised to 0.332. So here we can find out on that basis the average heat transfer coefficient from the Nusselt number formula. So H bar, that is average heat transfer, is equal to Nusselt number, average Nusselt number multiplied by thermal conductivity divided by characteristic dimension. Here in case of a pipe, the characteristic dimension is equal to the diameter of tube, that is outer diameter of the tube, is equal to 0.023 K divided by D multiplied by average Reynolds number raised to 0.8 multiplied by Prandtl number raised to 0.333. So the above expression valid. Now here the condition for this particular two expressions are, if the Reynolds number is in between 1 into 10 raised to 4 and 1 into 10 raised to 5, and Prandtl number is in between 0.5 to 100, and L divided by D, this ratio should be greater than 60, then we can use these two relations, or else we can use the further correlation on the basis of the friction factor. Now here we'll see the problems related to the pipe, okay, flow through pipe. When 0.5 kg of water per minute is passes through a tube of a 20 mm diameter, it is found to be heated from 20 degrees Celsius to 50 degrees Celsius. The heating is accomplished by condensing steam on the surface of the tube, and subsequently the surface temperature of the tube is maintained at 85 degrees Celsius. Determine the length of tube required for fully developed flow. Okay, so here we have to find out the length of tube at which the flow of the fluid becomes fully developed. So the thermophysical properties of water are provided. Okay, so rho is equal to 983.2 kg per meter cube. Cp is equal to 4.178 kilojoule per kg Kelvin. Thermal conductivity K is equal to 0.659 watt per meter degree Celsius, and kinematic viscosity nu is equal to 0.478 into 10 raised to minus 6 meter square per second. So on the basis of this particular statement, we can write the given data as m dot is equal to, that is mass flow rate of water, is equal to 0.5 kg per minute. Then diameter of the tube is 20 mm, that is equal to 0.02 meter. Temperature of the surface is equal to 85 degrees Celsius. Then inlet fluid temperature is equal to 20 degrees Celsius, and outlet fluid temperature is 50 degrees Celsius. Now, and the properties of a fluid are provided at a 60 degrees Celsius. Properties of water are provided at a 60 degrees Celsius. Now we have to find out the length for fully developed flow. So initially we have to check out whether these properties are suitable to our problem or not. So so that we have to find out the mean film temperature, because we have to consider the properties of a fluid at a mean film temperature. So here the mean film temperature is nothing but surface temperature plus fluid temperature divided by 2, that is the mean film temperature. Now here the fluid temperature, two fluid temperatures are provided, inlet fluid temperature and outlet fluid temperature. So for considering the fluid temperature, we have to take the average of inlet and outlet fluid temperature. So inlet fluid temperature plus outlet fluid temperature divided by 2 is the average fluid temperature. So 20 plus 50 divided by 2 is 35 degrees Celsius. So that will be our T suffix F, that is fluid temperature. So mean fluid temperature can be determined as by considering the fluid temperature as a 35 degrees Celsius and the surface temperature as a 85 degrees Celsius. We can write the mean film temperature as a 85 plus 35 divided by 2 is equal to 60 degrees Celsius. So properties of fluid should be considered at a mean film temperature and given in the problem, because the properties of a fluid are provided at a 60 degrees Celsius only. Okay, so take the thermophysical properties of water at a 60 degrees Celsius only. So we can consider these properties for this particular problem. Now first thing is nothing but we have to find out the type of the flow. So on the basis of Reynolds number only we can determine the type of the flow, whether this flow of the fluid is laminar or turbulent. So Reynolds number is equal to V multiplied by D divided by mu, that is nothing but velocity multiplied by diameter divided by kinematic viscosity. So here we don't know the velocity, so but mass flow rate is provided. So on the basis of a mass flow rate we can determine the velocity of the water. So mass flow rate is provided And mass flow rate formula is mass flow rate is equal to density multiplied by area multiplied by velocity, where this area is the cross sectional area. So the rho multiplied by pi by 4 multiplied by d square multiplied by velocity. Mass flow rate will be given as 983.2 multiplied by pi by 4 multiplied by 0.02 bracket square multiplied by velocity. So we have the mass flow rate in a kg per minute. So we have to convert that mass flow rate in a kg per second. So it will become 0.5 divided by 60. We'll get the, after calculation we will get the value 0.3088 multiplied by velocity. So this particular value will be considered as the average velocity. So v bar, that is nothing but average velocity, is equal to 0.02699 meter per second. That will be the average velocity. So average Reynolds number can be determined. Re is equal to v bar multiplied by d divided by nu, where the v bar is the average velocity, d is the diameter of the tube, and nu is the kinematic viscosity. We have to put all the values of v bar, d and nu over here. So 0.02699 multiplied by 0.02 divided by 0.478 multiplied by 10 raised to minus 6 will get the Reynolds number is equal to 1129.28. So this Reynolds number is very less than 2300, so that we can say that the flow is laminar. Now here the wall temperature is constant, so with constant wall temperature having fully developed a flow, we have to determine the length. So for the constant wall temperature having fully developed the flow, Nusselt number is equal to 3.65. Nusselt number is equal to 3.65. So and Nusselt number, we can write the Nusselt number equation as a h multiplied by d divided by k, where h is heat transfer coefficient, d is the diameter, k is the thermal conductivity. So h, we will get h is equal to 3.65 multiplied by k divided by d. So k value is provided in the property of water at a 60 degrees Celsius and diameter as 0.02. So we will get the we have to put these particular values in this particular equation. So we will get the equation 3.65 multiplied by 0.659 divided by 0.02, and we will get the h value as a 120.26 watt per meter square degree Celsius. Now we have to find out the rate of heat transfer by convection. So for that purpose, the two formulas we have to consider, that is nothing but heat transfer rate by convection, and the second thing is nothing but heat gain by the fluid. Okay, so the heat transfer rate by convection will be written as surface area multiplied by average heat transfer coefficient multiplied by surface temperature minus fluid temperature, okay, is equal to heat gain is given as a mcp multiplied by tf naught, that is outlet fluid temperature, minus tfi, that is the inlet fluid temperature. So we know that the surface area for the heat transfer, A suffix S is the heat transfer surface area. So surface area will be pi dl for the tube. So pi dl as a surface area multiplied by h, we have calculated average heat transfer coefficient as a 120.26 into, now here the surface temperature is 85 and the average fluid temperature is a 35. So we have taken 85 minus 35 is equal to mass flow rate is 0.5 divided by 60 multiplied by Cp value is 4.178 kilojoule per kg Kelvin. Here we have to convert it into a joule per kg Kelvin. For that purpose we have to multiply with 10 raised to 3, and Tf naught, that is the outlet fluid temperature, is 50 and inlet fluid temperature is 20. We have put up this here, and we will get the, after calculation we will get the 377.8 multiplied by L is equal to 1044.5. So we'll get the length is equal to 1044.5 divided by 377.8 is equal to 2.76 meter. 2.76 meter. This is the Now the second problem related to the flow through tube is here. A tube 5 meter long is maintained at 100 degrees Celsius by steam jacketing. A fluid flow through the tube at the rate of 2940 kg per hour at 30 degrees Celsius. The diameter of the tube is 2 cm. Find out average heat transfer coefficient. Here we have to find out the average heat transfer coefficient. Tube length is provided as a 5 meter and it is maintained at a constant temperature 100 degrees Celsius. Okay. Take the following properties of the fluid. That is nothing but rho is equal to 850 kg per meter cube. Cp is equal to 2000 joule per kg degree Celsius. Nu, that is kinematic viscosity, is equal to 5.1 into 10 raised to minus 6 meter square per second. Thermal conductivity is equal to 0.12 watt per meter degree Celsius. So given quantities we can write in this manner. The length of the tube is equal to 5 meter. Diameter of the tube is 2 centimeter, that is nothing but 0.02 meter. Mass flow rate is 2940 kg per hour. Fluid temperature is 30 degrees Celsius and surface temperature is 100 degrees Celsius. So by process we have to first of all find out the flow type. So for that purpose we have to determine the Reynolds number. So Reynolds number is equal to velocity multiplied by diameter divided by kinematic viscosity. So mass flow rate. Now here velocity we don't know. So for that purpose we have to consider the mass flow rate formula. Mass flow rate is provided as a 2940 kg per hour. So this particular mass flow rate we have to convert in a kg per second. So for that purpose 2940 divided by 3600, it will be converted into a kg per second, equal to, we know the mass flow rate formula, that is nothing but density multiplied by area multiplied by velocity, where this area is the cross sectional area. So for the tube the cross sectional area is pi by 4 multiplied by d square. So equation becomes rho multiplied by pi by 4 multiplied by d square multiplied by velocity. Now this mass flow rate, from this we have to find out the velocity. So we can write all the values of rho, a and m dot, so that we will get the value of velocity. So 2940 divided by 3600 is equal to 850 multiplied by pi by 4 multiplied by d square is the 0.02 square multiplied by velocity. Now we'll get the velocity is equal to 2940 divided by 3600 multiplied by 4 divided by 850 multiplied by pi multiplied by 0.02 square. So velocity we will get v is equal to 3.0582. So this velocity is the average flow velocity. So next thing is nothing but we have to find out the Reynolds number. Reynolds number is nothing but velocity multiplied by diameter divided by kinematic viscosity. So velocity is 3.06 multiplied by diameter is 0.02 meter divided by kinematic viscosity is 5.1 into 10 raised to minus 6 meter per second square, equal to, we'll get this Reynolds number as 1.2 into 10 raised to 4. Now this value is greater than 2300, so that the Reynolds number is in the range of a turbulent flow. So we can say that the flow is the turbulent flow. Next we have to find out the Prandtl number. So Prandtl number, we know that mu Cp divided by K. Now directly the dynamic viscosity value is not provided, but we know the kinematic value, kinematic viscosity value is provided as a given data, and also the density. So we know that the kinematic viscosity is equal to dynamic viscosity divided by density. So therefore the dynamic viscosity is equal to density multiplied by kinematic viscosity. So here we have put this value as equation for the mu. Mu is equal to rho into nu. Nu is the kinematic viscosity. So rho into nu multiplied by Cp divided by K is nothing but Prandtl number. Put all the values of this rho, nu, Cp and K, that are the given quantities. So 850 multiplied by 5.1 into 10 raised to minus 6 multiplied by 2000 divided by 0.12. So we'll get the Prandtl number as 72.25. and this Prandtl number is in the range of 0.5 and 100. Then the Reynolds number is in the range of 10 raised to 4 and 10 raised to 5. Then we can say that L by D is 5 divided by 0.02, which is 250, which is greater than 60. So we can use the formula for the turbulent flow as Nu bar, that is nothing but average Nusselt number is equal to 0.023 Reynolds number raised to 0.8 Prandtl number raised to 0.333. So and we know that the Nusselt number is nothing but H multiplied by D divided by K, that is HD divided by K is nothing but Nusselt number, and from that particular equation we can derive the formula for average heat transfer coefficient as equal to average Nusselt number multiplied by thermal conductivity divided by diameter of the tube. So we can easily determine the value of H bar as H bar is equal to 0.023 multiplied by K divided by D multiplied by Reynolds number raised to 0.8 multiplied by Prandtl number raised to 0.333. So therefore H bar is equal to 0.023. The K value is given as 0.12 and diameter is given as 0.02. Reynolds number we have determined as 1.2 into 10 raised to 4 and it's raised to 0.8 multiplied by Prandtl number we have calculated as a 72.3 raised to 0.333. So therefore H bar we will get as H bar is equal to 1052.8 watt per meter square degree Celsius. So these problems are related to the forced convection heat transfer, specifically for flat plate, flow over the flat plate, and the flow over the flow inside the tube. So these are the important problems. For more practice, refer the assignment booklets also, and if any doubt, please ask the questions. Thank you.